So far, the objects that we've studied have been sequences, and sequences are basically functions of n into r, which to each index, each position, associates the actual term of the sequence, the corresponding term of the sequence. But most of calculus isn't working with functions from n to r, it's working with functions from r to r. How do we extend this? How do we go from sequences to functions? Let A be any subset of R, and C a point in R, not necessarily in A. We'll say that the neighborhood V delta at C, where delta is some positive number, is an interval which consists of all of the real numbers which are such that their distance from C is smaller than delta. Write this using interval notation as C plus or minus delta, if you'd rather C minus delta, C plus delta. What's the link with A? Why do we need a set A? Well, we're going to say that C is a limit point, also sometimes called a cluster point, of A if every neighborhood V delta of C contains at least one point in A other than C. Now C is not necessarily a point of A, but it could also be a point of A. In any case, if every neighborhood of the point C contains at least one point in A, we will say that C is a limit point. Think about what this means. Of here a point C, potentially this could be A. For instance, it could be something more complicated, but it could be something. Now, there are going to be neighborhoods of this point C which contain points in A other than C. For instance, this neighborhood right here contains a bunch of points here that are in A other than the point C. There's other neighborhoods, though, around that point which contain no point in A. And so this point C here is not a limit point of the set A here. Whereas this other point right here is going to be a limit point of A because any neighborhood around the point, no matter how small, will at least contain some points in A here. Okay, so this one would be a limit point. This one here, not a limit point. Now the question you might have based on this drawing is, it certainly seems to be the case if this point C is not in the set A, it cannot be a limit point, and if this point is in A, it is going to be a limit point. Is this just an accident of the drawing? Is it possible for a point C, which is not in A, to be a limit point of A? We'll do an example here. Find the limit points of the following set. Consists of all the harmonic ratio, 1 over n, where n is a positive integer. Well, do we know what this set looks like? Here's 1, it is in there. Here I have 0. Well, I know that 1's in there, and I have 1/2, and I have 1/3, and 1/4. None of these points here. 0 is not in the set A, but all of these other points are. Let n be any integer. The distance between a point in A and the subsequent point. So perhaps this point in A here would be 1 over n, say, whereas the subsequent point in A would be 1 over n plus 1, say. Well, this distance is 1 over n minus 1 over n plus 1, which, you know, if you do common denominators, is 1 over n times n plus 1. Now, this is always going to be equal to 1 over n squared plus n, which is itself always going to be greater than 1 over 3n squared. Why is that the case? Well, because 3n squared is always greater than n squared plus n for all n. This is something you might want to show by inductions. So now I'm going to pick a delta to be 1 over 3n squared. That is greater than 0. Remember, I've picked a specific n here to be an integer. This relationship holds for every n, but I'm interested in the one where I've picked a specific n, somewhere here, for instance. Here's a sequent one. So I've picked this delta here. Let's look at the neighborhood of 1 over n with this specific